We've now finished talking about InSAR processing, so I'm going to move on and talk about some of the challenges and limitations for InSAR. We looked at a typical processing chain for mining, but for brevity I brushed over a few details. For instance, I've mentioned previously that the phase values are limited between 0 and 360 degrees, but we haven't yet looked at the implications of that. I also want to group together some remaining topics that we must talk about, such as image resolution, coherence, displacement sensitivity, and displacement direction. Finally, we're going to take a look at typical InSAR results for mining. We're now going to talk about a few topics that all relate to the fact that phase measurements are bounded between 0 and 360 degrees. Take this scenario for instance. 3.5 centimeters of displacement has occurred. The displacement is discrete in that the neighboring pixels are unaffected. Remember that InSAR is a spatial technique. Pixels have an inherent dependency on their neighbors for all kinds of processes. It's very difficult to say anything meaningful about individual pixels or even small groups of isolated pixels. Let's talk in terms of TerraSAR-X data in this example. The TerraSAR-X wavelength, or lambda, is 3 centimeters. But recall that our measuring stick is lambda over 2 to account for the fact that the signal travels to the Earth and back again. So the ground moving by 3.5 centimeters is like saying it moved 2.3 rulers worth, because 3.5 centimeters divided by 1.5 centimeters is 2.3. Now remember that for each pixel, the satellite only records the last fraction of a wave. We don't get to know anything about any of the whole wave cycles that preceded it. So all I recover from my 2.3 rulers worth of displacement is the 0.3 portion. And therefore my displacement measurement is 0.3 multiplied by lambda over 2, which equals 0.5 centimeters. So from 3.5 centimeters we only capture 0.5 centimeters in this scenario. For the confused, this is analogous to someone falling asleep at noon. They awake and the clock says 3 o'clock. Let's say they took some particularly powerful sleeping pills, and they don't know if 3 hours have passed, or 15 hours, or even 27 hours. They don't know anything about the whole 12-hour cycles that might have occurred. They can only measure the fraction, 3 hours. This is thankfully a rare scenario in InSAR. This is a much more typical displacement gradient that occurs. We can recover all of the displacement in this scenario by counting up the small fractional measurements for each pixel, joining the dots along the way to the highest displacing pixel at the bottom. This works because in this scenario, none of these small displacements exceed lambda over 2. This itself implies a kind of speed limit for InSAR, which is this. When adjacent pixels displace differently by more than lambda over 2, InSAR will underestimate the displacement. So for TerraSAR-X with 3 meter pixels, that's a displacement gradient of 1.5 centimeters over 6 meters. It also implies that there must at some stage be an algorithm that does this counting. If I know all of the phase changes for all of these little steps, it's trivial to sum them by eye and come up with a max displacement of 3.5 centimeters. But for efficiency, obviously we need an algorithm to do that, which we haven't yet mentioned. This neatly leads us to phase unwrapping. This actually represents the biggest challenge for InSAR processing. Consider the interferogram on the left. My background on average is light blue, which represents a displacement of 0. The displacement area in the center, I can by eye count 1, 2, 3 fringes. I know my lambda over 2 is 1.5 centimeters, so multiplying 3 by 1.5 equals 4.5 centimeters. So the area inside the third fringe has displayed around 4.5 centimeters. But think about what the data actually looks like. The phase values along the red transect line are plotted on the right, also shown in red. The red line shows the phase values climbing steadily, but when they reach 360 degrees, they of course plummet back to zero. This is expected, remember. We only record fractional cycles. What we want in our results, though, is the blue line. We want the processing equivalent of counting the fringes so we can recover values of displacement that are higher than lambda over 2, which is only 1.5 centimeters for Terrace RX. This is what phasing unwrapping is. It's an exercise in counting fringes. Except unlike the example here, it's done in 2 dimensions. And there are discontinuities in the data, like layover or water bodies and vegetation to deal with. This is a hard problem, but it's not intractable. When it goes wrong, we get underestimates for displacement. It's pretty hard to overcount fringes, so we don't really get overestimates. And when we reach our speed limit that we just mentioned, there is no unwrapper that can solve that without introducing some extra assumption. We simply don't have enough samples to solve the problem and characterize the real maximum displacement. Another challenge for unwrapping is to somehow teach the unwrapper to unwrap from the right direction. This area, for instance, looks pretty straightforward in an 11-day interferogram, shown in the top left. Except notice that the fringes on the top, left and right of the area all end abruptly. Only at the bottom is there a smooth transition rather than a jump. Remember our ambiguity slide. Jumps cause us problems. This jump is caused by displacement occurring along a distinct geological fault. To exacerbate the issue here, in longer interferograms, the area becomes much harder to unwrap, and after only 33 days, it's hard to even count the fringes by eye. And if we can't eyeball it, that usually means the unwrapper will struggle too. One more scenario related to unwrapping. This Sentinel-1 interferogram captured the SoCal earthquake in July 2019. Sentinel-1 has a ruler, or lambda, over 2 of 2.8 centimeters. So every fringe you see here represents 2.8 centimeters of displacement. So what's the highest magnitude displacement here? By eye, counting is easy at first, but then as the fringes get closer and closer together, it becomes much harder. You can envisage this as the gradient of displacement getting steeper and steeper. Eventually, counting becomes impossible, either by eye or using the unwrapper, because the gradient is so steep that one fringe lies on top of another. At this stage, the interferogram is aliased, and we have reached our speed limit, where adjacent pixels are displacing differently by more than lambda over 2. There simply aren't enough samples. In mining, if I saw an interferogram like this, I would suggest collecting images more often, if that's an option, because less time between data equals less displacement. This is a 12-day interferogram, but Sentinel-1 can potentially collect data every 6 days. But that wouldn't help here because all of the displacement was effectively instantaneous. So what else can we do? Let's briefly revisit this from an earlier lecture. The previous interferogram was Sentinel-1, which is C-band, and therefore one fringe equals 2.8 centimeters of displacement. But L-band is much longer. I need a whole 12 centimeters of displacement just to get one fringe. And it just so happens that the SoCal earthquake was also captured using L-band. Straight away, you should notice that there are far fewer fringes now. Our unwrapper is going to have a much easier time with this, and will give us an answer that is less precise because it's a coarser measurement, but ultimately it will be more accurate in the highest displacing areas, and much nearer the true value of displacement.